Please welcome Adam Tornhill.
Tack. So, once again, good morning everyone, and welcome to this session on how we can guide refactorings with something I call behavioral code analysis. Before I get to that, I would like to take a few minutes and reflect upon the human potential. Because I started to think about this just the other day, all those amazing, wonderful things we humans have achieved. And I mean, already thousands of years ago, we managed to erect the pyramids. In more recent times, we have made amazing scientific breakthroughs. We have managed to sequence the human genome. We have performed grand engineering projects. We have landed on the moon. And I'm pretty sure that these advances into the scientifics of what's possible will continue. And in the decades to come, we might see things like we will be able to tame fusion power and obtain clean energy. We might even revive the dinosaurs. How cool wouldn't that be? Right? We could build a theme park or something. But as a psychologist, I'm much more interested in what the limitations are. How far can we really push those boundaries? What are the boundaries of the human potential? And there are some things that I'm pretty sure that we will never be able to understand. One of my favorite examples is this, human consciousness. We will never solve that, I'm pretty sure. However, that doesn't mean we won't try. And there's actually active research going on in that very area right now. But then, of course, you have the other kind of problems where we know up front that this is just impossible. We won't even try, we won't even go there. And one example on that could be something like this. To modify someone else's code. And I'm only half jokingly now, because I do think this is a hard problem. And the reason I think it's a hard problem, it's because it's a constant uphill battle. And it's an uphill battle that I think is well captured in something called Lehman's laws of software evolution. So Lehman's laws are fascinating because, first of all, there are not any real laws in the formal sense of the word. No, they are rather accurate observations written down in the 1970s by Manny Lehman. And I would like to show you just two of those laws. And let's see if that resonates with your experience. So the first law is the law of continuing change, where Lehman says that a system has to continuously evolve and adapt, or it will become progressively less useful over time. So I think this is something you all recognize, right? This is the reason why we keep adding new stuff and new features to our existing products. We need to keep them relevant to our users. We need to respond to their needs. What I find fascinating is that there is some contrast to the second law of software evolution. And that second law is the law of increasing complexity, where Lehman says that as our system evolves, they will become progressively more complicated unless we actively work to reduce that complexity. Do you see the conflict between these two laws? On one hand, we have to continuously adapt and improve and add stuff to our projects, but as we do, they become more and more complicated, which means it becomes harder and harder to expand and improve on them. So this is a vicious circle that we need to break. And we need to break it by controlling the complexity. And Aslam did this wonderful presentation on how you can control and improve and by really understanding the true problem you're solving, the essential complexity. I would like to talk about the other kind of complexity, the accidental complexity. And what I mean with accidental complexity here is just the parts of the solution that are more complex than what the problem calls for. And I've found that in general, accidental complexity tends to come in two different shapes. On one hand, we might have complex parts of the code. So these are the parts of the code. It might be a module, file, or class, where the implementation is more complicated than it could be. There's an easier way to solve that problem. And then we have the second kind of complexity, where we have complex interdependencies. So in this case, each one of those parts may well be easy to understand in isolation, but the emerging system behavior is anything but simple. So I guess this kind of complex interdependencies is something that we start to see more and more. Think microservices, for example. That's what's happening there. And in this session, we're going to cover both of these cases. And we're going to do it by exploring something called behavioral code analysis. So in a behavioral code analysis, there's much less emphasis on code and more emphasis on the actual behavior that led to the current code. That is, we want to look at the evolution of the software. We want to look for patterns in the organization that builds the system. And in order to pull this off, we obviously need some kind of behavioral data. So where can we find that? Well, those of you who have attended my previous sessions or maybe even read one of my books, you know that I'm a big fan of version control data. I guess we just all have our odd hobbies, right? So the reason I'm so fascinated by version control data is because historically, we have used version control more or less as a complicated backup system and occasionally as a collaboration tool. But then, almost as a side effect, we have created all this wonderful behavioral and social data. It's just waiting to be mined. So that's what I want us to do today, to mine version control data and see if we can uncover any patterns in how we as an organization works with the code, and use that resulting information to guide our decisions. When I do a behavioral code analysis, I also tend to prefer simple metrics. And the reason I prefer simple metrics is because metrics are never a guide. They never replace anything. They never replace our expertise. The metrics are just there to help us focus our attention on the parts of the code that seems to need it the most. So that means we need to extract that signal with the human in the loop. And what a behavioral code analysis offers is that if you take a typical large-scale system, it will contain its fair share of accidental complexity. And we cannot attend to all of that complexity at once, neither should we. So with behavioral data, it helps us take that large, complicated code base and narrow it down to a few parts where we can actually focus our human expertise. So what we're going to do today is that we're going to view complexity through the lens of behavioral data. All right, let's try to make this specific. I want to present a number of case studies for you. And my first case study is a code base that I think a lot of you actually carry around in your pocket right now. I'm talking about Android. More specifically, I want us to look at something called a platform framework base in Android, which is a pretty big code base. Consists of around 3 million lines of code. Most of it is implemented in Java, and it has been developed by more than 2,000 unique contributors. So what you see here is a visualization of Android called a hotspot analysis. And those of you who have attended my previous presentations will get a little bit of repetition here. And that's because I found that the hotspot analysis is fundamental to behavioral code analysis. That's like the starting point. So it's really important that we all understand what we see here. So in a hotspot analysis, first of all, it's a hierarchical visualization. It's a visualization style called enclosure diagrams. And it's a hierarchical visualization, which means it follows the folder structure of your code. So if you have a look at those circles that blink right now, you will see that each one of them represents a folder in your code base. It's also an interactive visualization, which means we can click on it and zoom in to the level of detail we're interested in. And if we do that, we see that once we get to a lowest level, each file in that code base will be represented as a circle. And you see that those circles have different size. That's because size is used to represent something I call code complexity. What is code complexity? Well, in a minute, I'm going to show you how I measure it. But before I go there, I would like to point out that just because something is complicated, right? So the larger a circle, the more complex the code. But just because something is complicated doesn't mean it's a problem. It's only a problem if you need to deal with that complexity. So we need to find out if that complexity actually affects us or not. And this is data that we can pull out of a version control system. So we can look at things like change frequencies. How often do we actually need to do some work in that part of the code? And the more often, the more red the corresponding file here. So you can view code change frequency. It's basically like if you have some technical depth in that part of the code, the change frequency of that code is like your interest rate on that technical depth. And the combination of those two dimensions is what I'm referring to as a hotspot, complicated code that you have to work with often. Now, how do I measure code complexity? I guess that most of you are familiar with some other complexity metrics. You might have heard about things like McCabe's cyclomatic complexity. You might have heard about nesting complexity metrics. You might have heard about things like cognitive complexity. And what all of those different ways of measuring code complexity have in common is that they tend to focus on this. They tend to focus on properties of the code. So they typically look for things that put a cognitive load on our mind. So things like conditional statements, loops, all that kind of stuff. But I will claim that there's a much, much simpler view of code complexity here. And it's a simpler view that we can learn about by studying visual artists and learn about the concept of negative space, the power of what's absent. So this is a different view of complexity. We can really just calculate the number of indentations in our code. And it sounds like a crazy idea, but if you look at it, our indentations are never random. So it turns out they have a very high correlation to the actual code complexity, things like nested conditional statements. And indentation-based complexity like that also has the advantage that it's language neutral, which means we can use the same metric for all kind of programming languages. And it's simple. So let's go with indentation-based complexity and see where it takes us. So let's go back to Android. The number one hotspot in Android right now is a module called Activity Manager Service. Wow, isn't that a wonderful name? So let's reflect upon that a little bit. So on one hand, we have activity. That sounds like it could be something from the problem domain. It probably is. And then we have two words, manager, service. And each one of those in isolation signals a module with low cohesion. If we combine them, and we combine them with the fact that we have 20,000 lines of code in that class, we might start to suspect that we might have a problem with too many responsibilities there. Just a wild guess. Now, the next thing we want to know when we explore code like this is that what happens to that hotspot over time? Is there a potential problem that we as developers who work on that system know about so that we've started to make improvements to it? Or is it code that just gets worse and worse? One technique I use for that is something I call complexity trends. So what I do here is basically I just pull out each historic revision of that hotspot and then I measure the indentation-based complexity at each point in time. So that's what I visualized with the red line here. And the advantage again with indentation-based complexity is that it's so fast, we don't even need to parse the code, we can just calculate indentations. And then I plot the blue line, which is the accumulation of lines of code over time. And what we see here is basically that this is a growing problem. We see that that code, it keeps accumulating lines of code, but the complexity seems to grow at an even steeper rate, which might suggest that new code is added in the shape of nested conditional logic, things that are really hard for a human to work with. So I would say that based upon this data point, it's quite probable that the organization behind this code base would benefit from doing improvements to that hotspot. However, even if we know that this module should be refactored, we just cannot start to change it. And the reason we cannot do it is because there's always going to be a trade-off between doing improvements versus new features. And that becomes obvious with the scale of a system. So let's take a different look at the code base. Let's look at the social side of the code. Because the wonderful thing with using version control data is that it's actually social data. It contains information about exactly what programmer that wrote which lines of code. So what I did now was that I went to the Android repository and I pulled out information about that and I looked at how many developers have touched this hotspot over the past 6 months. And I visualized that using a technique called fractal figures. So in this figure, each colored slice represents the relative contributions of a developer. And what you see here, if you count them, you find out that you actually have 74 different authors that have worked with that code over the past 6 months. So that means if we want to refactor that code or we want to make some larger redesigns of it, we just cannot branch out and start to work in isolation for 3 months because we will never, ever be able to merge that back. So we need to take social factors into account in our redesign. And this is quite a common problem. And it's a problem I worked with a lot over the past years. So what I tried to do was to formalize some of the approaches I use. And in this case, I would apply something I call the Splinter Pattern. So what is a Splinter Pattern? Well, the idea behind a Splinter Pattern is that it provides a structured way to break up hotspots into smaller and more manageable pieces that can then be divided among several developers to work on in parallel. Let me show you an example. Let's take our Android hotspot here, the Activity Manager service. You see a thin slice of it here. Now, I said that the data indicated that we might have a problem with cohesion here. So the first thing I do in a Splinter Pattern is that I identify the different responsibilities inside that code. And you might find out that you have things like a stack behavior, you have some translucence behavior, you might have some ownership behavior, and so on. And what I do next is that I take one of those behaviors, I take all those methods related to it, and I copy-paste them. Literally copy-paste them into a new file and try to put a sensible name on it. After I've done that initial step, I commit this code and I push it. And the reason I do that is because so far this is a completely safe code change. We haven't really modified anything, right? We just duplicated some code that isn't even used. So this is safe. The next thing I do after that is that I return to the original context and I rip out all the implementation, all the code from each one of those methods, and I replace them with a simple delegation to my new Splinter. And the reason I go through this extra step is because I want to maintain the original API as long as possible. And I want to maintain that in order to avoid that my local changes start to ripple across the system and influence other parts of the system and the organization. So once you have done that, you continue with the other behaviors. And you will find out that even though you haven't really improved the code in this initial step, you have a completely different context that kind of makes it possible to start to do larger improvements. So first of all, what we have done here is that we have isolated the different behaviors, which means I can start to improve and refactor the code in one of them with a minimum of disturbance to the rest of the organizations. So my colleagues can continue to add new features to the other stuff. And this is a big win. And the reason we have that win is because we now have created a much better alignment between the problem and the solution domain. And I have found that when we manage to pull that off, when we manage to align the problem and solution domain, we also manage, almost as a side effect, to create natural boundaries for all those other 74 authors that work on that code. So organizational design and software design go hand in hand all the time. Now, let's say I've started to refactor the activity stack and I start to get satisfied with where it took me. The next thing I do is that I return to our original context. Remember, we had all those delegating methods. And I just cut out the middleman. I rip that out and I let the clients access my new splinters directly. A splinter refactoring is an iterative process that may stretch over months depending on how big and complicated your hotspots are. And like all long-running processes, it's really important to get continuous feedback. So one technique I've been using for that is the complexity trends. So what you see here is an example of a real-world splinter refactoring. So this is a hotspot that accumulated a lot, tons of complexity over the years. And then we started to apply the splinter, and you can see that the complexity starts to drop. And the reason I find this important is because, first of all, if you work with it with something, any task, for a long time, it's really motivating to get that feedback, to see that your actual efforts has a real impact. And there's a second aspect too. I have found that these kind of complexity trends, they work really well to show progress to non-technical stakeholders as well. So it might help non-technical people to peek into our otherwise inaccessible technical world of code. Now, when I did a splinter refactoring here, I kind of said, all right, let's pick one of those behaviors, let's extract it, and let's start to improve that. But the question is, of course, where do we start? We have 20,000 lines of code in that hotspot. So one technique I want to show you, and this is something I use when I come across those large hotspots, is a technique I call hotspot X-rays. So what I do here is that I take that hotspot and then I parse it into different functions. And then I look at the different commits and see which functions do each commit hit. And that makes it possible to calculate hotspots on a method level. Let's have a look at Android and see how it looks there. So these are the method level hotspots in the Activity Manager service right now. And we see that the number one hotspot is a method called handle message. And we see that there has been tons of development activity just over the past year. In fact, 97 commits over the past year. And we see that that method has grown to 500 lines of code. That's quite a lot for a single method, isn't it? We're going to return to handle message in just a minute. But before I go there, I would like to point out and give you some pointers to the kind of tools I use in case you want to try it on your own code. So when I started to work with these techniques quite a few years back, and when I wrote my first book, there weren't really any tools available that could do all those kind of analyses I wanted to do. So I started out by writing my own tools. It's a project called CodeMat. It's still available on GitHub. I still do the occasional maintenance on it, so it might be one starting point. The tooling I work on right now is called CodeScene. And CodeScene automates all of these steps. So it's basically you press a button and you start to inspect the analysis and starts to extract the information from it. CodeScene is also free for open source, so please have a look at it. Finally, I'd like to point out that it's quite fascinating that you can get really, really far with Git itself. So one thing you can do is you can actually run git log with the -l flag from a command line, and you can trace the evolution of an individual function, which is basically something that you can build an X-ray upon. All right. I'd like to continue by talking a little bit about code application. So let's start by asking all of you, how many of you have run a copy-paste detector on your current code base? Not so many, like 5, 6 hands. Wow. This is kind of like the common response rate I get when I ask that question. And I find it fascinating because copy-paste detection is an old idea. It's an idea pioneered by Brenda Baker back in 1992. So it's a long time ago. And yet copy-paste detection never really took off. It never became mainstream. And I think the reason for that is because the results are way too depressing. In fact, if you look at the research, you will see that somewhere between 5 to 20% of all code is duplicated to some extent. That's a lot of code, isn't it? And we can kind of see that if we return to handle message in Android. Remember, a method level hotspot. So again, this is just a small part of it, but we can pretty much see that there is definitely some duplication of knowledge here. There is a process where the same pattern occurs over and over again. Now, imagine you have 500 lines of code like that. This is going to be really, really hard to work with. But of course, if we want to change that copy-pasted behavior, your changes will ripple across the different function blocks inside this method. And besides, it's quite likely that we will make a mistake because we won't get any help from the compiler either. So one thing I do, once I come across code like that, the first thing I do is I look to break it up. And I look to break it up by starting to identify commonalities that can be abstracted away to modularize the design. So what I did in this case was I implemented I took all the commonalities, extracted a method that I call execute, and then I just parameterize it with a small behavior that varies across the different invocations. And one advantage of this is that once you start to modularize those large hotspot methods, you start to reveal the overall algorithm. And that in itself lets you see new abstractions, which means you can simplify even more. So in this case, once I've extracted those execute methods, the first thing I noted was that, hey, this looks like I could actually turn it into the design pattern command, which would let me encapsulate everything related to each message in its own object. And if I do that refactoring, the whole handle message method will eventually just go away. And I have one problem less in my code base. Now, when I talk about code application, I feel that I should let you in on the dirty secret of copy-paste. And the reason I want to talk about this is because I think that we as developers, we are conditioned to despise copy-paste code. We have learned it's a bad thing to do. It's naughty. We don't do it. And I think that's a problem because copy-paste in itself is not an issue. Let me give you a few examples. So let's say I have some code over here, and I copy paste it over here. And now those two copies evolve in different directions. In that case, I would say copy paste was the right thing to do. Or let's say I have some code over here, I copy paste it over here, I never need to touch those copies again. Again, copy paste might have been the right thing to do. The problem is that we cannot tell this good copy paste from the bad. So let's say we copy paste some code over here, and now I have to make a predictable modification each time I modify one of those copies. That's where copy paste starts to become expensive and dangerous. So we need a way to sort out the good from the bad copy paste. And one technique I've been using for that is something I call change coupling. So let me show you the concept. So let's say we have a file here, and I need to go into it and make some kind of change. So I change the methods A and B together. The next time I modify that file, I change something else. And the third time, I'm back to modifying A and B together again. Now, if this is a trend that continues, there has to be some kind of relationship between A and B here, because they change together all the time. This is change coupling. Change coupling is about those patterns that emerge over time. And change coupling is something that we can use to prioritize copy-paste. And I want to show you an example from a fascinating code base, the Linux kernel. And please look carefully now, because this is a rare sight. This is 16 million lines of code. What's even more fascinating is that those 60 million lines of code are written by more than 15,000 contributors. So this is social design at scale, and I'm really impressed by the Linux kernel. To me, this is an engineering achievement that's just as great as landing on the moon. The Linux kernel, of course, also has its hotspot. And one of my favorite hotspots in the Linux kernel is something called the Intel display. So this is a driver for the Intel graphics cards. And we can pretty much see here from the data that it's a pretty big file, right? Around 11,000 lines of code. And we also know that the quality of that code will impact us as an organization, because we've done more than 3,000 commits to that file. So there's a lot of change there. And if we inspect the trend, it reveals that, again, this is code that just keeps accumulating complexity. So that means the part of the code where we need to spend most of our time, as we do that, it becomes harder and harder and harder. Remember Lehman's laws. This is a trend that we need to break. And one way of approaching that is looking for really low-hanging fruits. Things like duplicated code that we can remove. So what I did here was that I looked for change coupling between the different functions inside Intel display. And I would like to present just two of those findings to you. In the first case, we have something called Intel finish page flip, two different methods with similar names, and we see together from the data here that they change together in 100% of all cases. So you modify one of them, you have a predictable modification in the other one too. And a possible explanation for that is given in the right-hand side column that says similarity. Ah, that's a copy-paste detector. 99% similarity. Wow. Let's look at the code here and see if we can spot the differences. Are you ready? You do look ready. Here we go. Have a look at this beauty. You don't really need to be a C programmer, right, to detect the differences. That's a single character difference. Wow. So this is the kind of code that should be relatively simple to just get rid of the duplication, introduce a shared abstraction. So this is actually not that interesting. It's something we just fix as we go along. But I would like to point your attention to the second kind of change coupling here, because this one worries me much more. Now we have two other methods, something with find best DPI, and again, they are coupled in time 100% of all changes, but their similarity is only 95, so it's a lower code similarity. Interesting. Let's look at the code. Now, as you see here, there is some kind of condition here that's present in the left-hand side version, but not in the right-hand side version. And this worries me, because when I come across this code, I have no way of knowing, is this a bug that I fixed in one version, but forget to fix in the other one? Or is it a context-specific check, something that can only occur in that calling context? Without more information, I just cannot tell. And what that means for our abilities to maintain this code is that we're going to spend an insane amount of time just trying to understand why that check is absent in the other version. So this is the kind of copy-paste that's really expensive. And the way we found that was by combining copy-paste detection techniques with change coupling to kind of prioritize the code clones that really, really need refactoring. And if you want to try out change coupling, you can look at the tooling I had earlier. If you want to try out copy-paste detection, which I really recommend that you play around with, have a look at tools like Clone Digger and Simian. Both of them are excellent alternatives. Now, I would like to take it a step further and actually claim that code application goes beyond code similarity. It goes a little bit deeper. And this time, I would like to look at a different code base, a .NET code base, Entity Framework Core. So how many of you are actually using Entity Framework today? So some of you, like 10, 15, cool. So it's a smaller code base, just around 500,000-600,000 lines of code. And what I did was now, again, I identified a hotspot, which turned out to be a unit test suite, and I looked for change-coupled unit tests. And what I found was this. So what we have here are two different unit tests. One of them is called string starts with method call, and one is called string ends with method call. They have a change coupling of 100%. They always change together. Now, Entity Framework is an object relational mapper. So what they do in these tests is that they kind of set up some condition, and then they generate a SQL, and they provide the expected SQL in the unit test. So they look that they get the expected results back here. And if you look at the SQL, again, you will see that it's very similar. The only differences are in the where clause. So again, we could take that, all those similarities, we can abstract them away, maybe into a method of their own. We could even introduce a string constant or something like that, and we can reduce the amount of duplication in our code. Would that make the code better? No, it would make it worse. Because those unit tests, those are intended as I find that they serve really, really well as an entry point to a new code base. So they are there to communicate what actually happens once I run that code. And once I start to abstract too much away from them, there's kind of a tipping point. And beyond that point, the more I abstract away, the harder it becomes to read the code. So by refactoring away that application, we would actually make the code worse, not better. But still, we have these duplicated chunks of code. So what I would like to do is to kind of put a mental post-it note on the code and say, hey, this stuff is duplicated. I know about that. It's deliberate. But please remember to change both of them together. How can we do something like that? Well, we can take some inspiration from a field of psychology that James introduced earlier this morning, Gestalt psychology. So the Gestalt movement was something that started in Germany in the 1920s. And there were a set of psychologists that set out to formalize a bunch of rules and principles for how we humans perceive the world. And one of those principles was something called the principle of proximity. And the proximity principle states that objects or shapes that are close to another appear to form groups. This is something you can see yourself. Let's do a small experiment here. Have a look at the following figure. How many different groups do you see? How many of you see 4 groups? I think that's a majority. That's the typical answer. Might be interpreted differently. But the fascinating thing here is, of course, if you look at the details, you see that there are a bunch of circles, right? And you have the same number of circles on the left-hand side as on the right-hand side. So it's just the spacing between them that make them appear as groups to us. Now, the proximity principle is something that marketing people love. Designers love it, so you will see it in a bunch of different company logos. It's also a principle that I think we can use when we refactor code. So, to give you an example here, let's say we have 2 different versions of a program, and we want to make a change. The first time in case A here, we modify 3 adjacent functions. In case B, we also modify 3 functions, but now those functions are located in different parts of the file. I will claim that change B, even though it's the same amount of code, is a harder change to make. So by pulling stuff that we expect to change together close to another, we help to communicate that it also belongs together, and it's a powerful reminder to the programmer, and more important, the code reader. So if I return to those 2 unit tests in Entity Framework, and you look at the whole file, you see that there are 50 lines of code between them. more important, there are 3 other unit tests interspersed between them. So I would refactor this for proximity and just take one of the methods and move it next to the other one to signal that they belong together. So far, I talked about change coupling between functions in the same file. But change coupling is a concept that expands to whole clusters of files to different subsystems. And when you do a change coupling analysis on a file level to find out which files are actually modified together, you will find that you get a lot of data, a lot of results. And that's because you always have a lot of expected change coupling in your systems. So you might have things like a unit test that change together with your application code. That's something you would expect, right? That's the change coupling you want. So what I use to narrow down the data to the interesting points is something I call the heuristic of surprise. So when I inspect a change coupling result, I look for surprising findings. Change coupling where I don't have a good explanation on why it's there. Things that might violate my architectural principles, for example. And I would like to show you an example from a really high quality code base, JUnit 5, that I think a lot of you are using in your daily work. And the reason I want to look at JUnit 5 is because if you pick up that code base and you look at the main hotspots, you see that the code looks good. It looks really, really good. So what I wanted to do was to see, can we detect some kind of opportunity for improvements by looking at change coupling and uncovering something that we cannot see from the code itself. So what I did here was I looked for change coupling between different files. And then I applied the heuristic of surprise and looked at what sticks out, what's surprising to me here. And what I found out was that there are 9 unit tests here, those that are highlighted in red. 9 separate unit test files, and they change together to a very high degree. They change together in more than 70% of commits that I do to any one of them. So this was a bit surprising to me because those 9 unit tests, they don't have any direct dependencies between them. They are distinct test suites. So the next thing I did to dig deeper was that I looked at change coupling on a method level. And here's what it looked like. Now, it looks a little bit noisy, doesn't it? So let me explain it to you here. So you see those colors on the outer side of the circle. Each one of those colors signals a group of method inside a specific unit test suite. And each one of those slices represents one method and it's change coupling to methods in potentially other files. So it's still a lot of different methods that keep changing together across that cluster of files, but at least we managed to narrow it down to the level where we can actually start to look at the code. So let's do that. Now, what I find fascinating here is that if you look at those unit tests in isolation, all of them look good. But we do see that there is some kind of repetitive pattern that repeats across them, which might hint at an abstraction that's just begging to come out. So let's run with that and see where it takes us. So what I would try in this case is that I will always look for cases where I have multiple assert statements next to each other, and then I try to introduce an abstraction for that by, again, abstracting away the commonalities. So I would have tried to change it for something like that. In this case, I try to use the builder pattern to come up with a kind of a fluent API. And I have found that with sensible default behavior, we can get rid of a lot of code this way and also help to minimize the change coupling across clusters of unit tests, which is a really common issue in the real world. But that's not the main point, because I think that the big win here is that we get our tests to express and communicate in the language of the domain. And to express tests in the language of their domain is one of the things I learned over the past year, that it's really, really important. It made a huge difference to me. And I do think that generic assertions are at odds with that goal. So I came to view unit test frameworks as a basic building block rather than something that I expose on the application level. All right, the final thing I want to talk about today is how the cost of those implicit dependencies increase with architectural distance. And the reason those costs increase is because the amount of surprise to us as a software maintainer increases with architectural distance too. And so far, I've ripped through a number of open source projects, so I think it's only fair that I start to criticize my own code too. So this is a piece of code I worked on the last year. this is a part of the implementation of CodeScene itself. And when I looked at this one, I found a surprising finding here. And I'm going to explain why it's surprising. But first, I want you to note that what actually happened here was that we had a part of the UI code written in JavaScript that kept changing together with a bunch of modules implemented in Closure in the analysis part of that product. And what was surprising about this was that I knew that the architecture looked something like this. So we have an analysis pipeline that's located in one Git repository. We pull out data from Git. And the UI part has quite some architectural distance from that analysis part. So this was surprising to me. Before I explain that, maybe you would like to know how can you track changes across different repositories? Wasn't change coupling about things that changed in the same commit? It is, but you will find that many organizations use something like a ticket ID or task ID system on top of Git. So you must stamp things like the Jira tickets inside your commit messages. And in that case, you can use the commit messages to relate different commits in different repositories to each other. You can identify logical change sets and calculate change coupling on that level. And this is a technique I found really, really useful to uncover change patterns in multi-repo projects, like, for example, microservices. Now, let's go back to the surprising finding here, where some analysis part of our code changed together with a part in the UI. When I looked at the actual methods, the change couple methods in JavaScript and Closure, by the way, this is one of the advantages of version control data, that it's language neutral, right? So we can uncover those dependencies across different technologies. And what I found out here was basically what happened was in the Closure part, when I added some new stuff to the analysis, maybe I extracted a new property from Git, then I populated a result structure. And each time I added something to that result structure, the UI had to be changed too to reflect that change. And I think this is a pretty common problem in many web applications. And it's something we try to solve with techniques like, for example, composite UIs, where basically you take away most of the details from the UI and instead you let the backend kind of populate the UI with the view model that kind of knows and explains how to render it. And a composite UI would solve this problem too. It would break the change coupling and make the change patterns simpler. However, I think the fundamental problem is a little bit deeper. So I would like to leave you with a thought here. Because I think what we actually have here is, even though those modules are in different repositories, they really shouldn't be, because they're part of the same logical component. The division into different repositories is really just accidental based on technical boundaries. And I think if there's a common theme in this presentation, it has to be that we should really let features drive our architectural building blocks, not technology. And I do think that the behavioral code analysis has a lot to offer here, because a behavioral code analysis will give you those insights that you cannot get from the code alone. And as such, these analyses help you focus your expertise and your attention to the parts of the system that need it the most. Now, before I leave you with some references, I'd really like to take this opportunity and say, first of all, thanks for inviting me, and thanks to all of you for listening to me. Take well care of your system, and may you code in peace. Thanks.